All right, we're on video 1, 2, 3, 4, 5. Video 5, we're nearing the end. So now we're going to talk about um, nonlinear volume distributions. Now, we've already talked about the fact that there can be nonlinear binding, which is really at the key of this, right? So nonlinear binding is what causes the nonlinear volume distribution. We know that drugs in the plasma are bound to AAG and albumin. Those are the two major binding proteins, as you might remember. And we see nonlinearities seen at 15 micromolar, um, which we see that with disopyramide, which is a class 1A antiarrhythmic, and with other drugs. We see nonlinearities with albumin at 120 micromolar for valproic acid and naproxen. So these are all in the therapeutic range where we see nonlinearities, where we see the drug overwhelming the plasma proteins that are available for the drug to bind to. Again, I apologize for this swoop. It should be straight across. So we know that the volume of distribution is equal to the plasma volume plus the tissue volume. Sorry, this should be subscript. I thought I did that, but I guess I didn't. Um, times the fraction unbound in plasma over fraction unbound in tissue. So volume of plasma, volume of tissue times the fraction unbound in plasma over fraction unbound in tissue. If we have nonlinear fraction unbound in the plasma, what's going to happen? The fraction, as the drug overwhelms those protein binding sites, this is going to increase, isn't it? Let's see if I can draw that on there. This is going to increase, which causes the volume to increase, but not until the concentrations are higher than the KD, right? So you'll see it at lower concentrations, it'll be linear, and then it'll become nonlinear at higher concentrations. So our volume distribution will increase with nonlinear fraction unbound in plasma, won't it? As you overwhelm those plasma protein binding sites. So what will happen? You'll see an increase in the fraction unbound and therefore the volume distribution. So fraction unbound will increase with increasing concentrations, therefore the volume of distribution will increase with increasing concentrations. What if there's nonlinear fraction unbound in tissues? So in this case, as the fraction unbound in tissues, it will increase as it overwhelms those binding sites. I don't know of any clinical example of this, so this may be moot. But as this increases, we'll see the volume distribution decrease. Again, at lower concentrations, it's linear, and then it becomes nonlinear once that the KD and concentration that's in the denominator there once this concentration becomes in the same range as KD, it will start to, as the concentration increases, the plasma, the tissue binding sites will be overwhelmed, and the fraction unbound in tissue will increase, won't it? So, same idea. What happens? The tissue binding sites, as they become saturated, fraction unbound in tissue will increase, and with increasing concentration, the VSS will decrease with increasing concentration. So you can see how nonlinear plasma or tissue binding will cause either an increase or decreasing with volume as the concentration increases. Usually it's flat though, right? Usually there's no concentration dependence. All right, that's it.